As Gabriele introduced me, I'm part of Nanophysics and Nanoscopy group at IIT, and in our group, actually, we have the Nikon Imaging Center. I'm managing such a facility. It's a joint lab between IIT and Nikon, and this is also, let's say, a service somehow that we provide to all the community, Italian, European, and worldwide. And this is actually, so it allows us to show, of course, Nikon instrument, but also our development. And so what we are really develop as method, as you saw also partially from Alberto and partially what I'm going to talk today, and other things that we do in the lab. And this is also possible not only thanks to Nikon, but also to the network we are part of, like Aeroba Imaging, that we are a piece of the Italian node. So we can also host people, any from you, for instance, to our lab to do experiment with our microscope, from commercial to our customized one. And of course, as the aim of the institute is also to transfer this technology not only to let's say a company like Nikon, Leica, or whatever, but also we made our startup company, as you already heard from Alberto. So my talk today will be anyway focused on super resolution, and in particular on the one that is, let's say, deterministic and let's say targeted, if you like. So on the STED fashion, as you already heard also from Johan. In general, more in general, we can say that we are doing, when we do super resolution, one way to describe it is to say, well, we do an on-off game in which we move from a fluorescent state, for instance, in the case of fluorescent molecule, to a dark state. And we can play these with light, and we can play these at molecular resolution, a molecular level, let's say. So anyway, although we saw already many, that let's say the key player of this game is fluorescent molecules, of course we can play with many other available states in the matter. And so, in fact, during my talk, I will also talk about absorption, for instance, as a way, as a state to work with super resolution. So, as I say, I will show mainly a STED fashion approach in which we have a scanning, so a deterministic scanning, in which so if you compare with the most known confocal scanning, we introduce a second beam, and so I don't have to say so much because you already heard about that. And the second beam acts to reduce the excitation spot, or better, where the spontaneous fluorescence can happen, to its center by stimulated emission, by saturating this phenomena. So you increasing the power, you get as narrow as possible spot of fluorescence. So the fact that you are playing, in fact, with the power, and actually not only with the power, but also with the shape of the zero that you can produce on your sample, the STED microscope is extremely flexible, and you can tune the resolution as you like on your sample. So not necessarily you have to go always for the maximum resolution, full power. That could be also, as you may understand, very could be even phototoxic. But this is, a possible drawback if you don't choose, if you don't perform the experiment as you really need to do. And so, as you can see here, you starting from the bottom, where you have just confocal and going up with the power, you can tune the resolution. But since we can build our microscope, we can build as flexible as possible. We can play with different shape of the donut. We can do the bottle beam, so the donut in the third dimension. So we can tune now also the shape of the resolution that we want and the volume that we would like to emphasize and to quantify the objects on our sample. So as you can see, instead of doing so this is the XY and this is the XZ and YZ, and you see that if you do only the donut, you get practically no resolution on Z, but you can apply a lot of power along Z and less along XY, and so you get improvement in the Z or a mixture of that, and so you can perform this kind of tuning. And of course, here we also try to study how to implement a new way to do this kind of three-dimensional confinement in order to reduce the power we need for improve the resolution and to make it as easy as possible and also as most robust. So also in the way to go deeper in the sample, you would like to keep this confinement as deep as possible. And so we are trying now to use the donut as the only let's say shape that we want to use also to perform the 3D improvement by tilting two donuts, for instance. And this is just a preliminary image. And this so we can now make all the nice images, let's say on regular sample like this, and we can do in 2D and in 3D. And of course, now we have a tool to investigate at the nanoscale, also to not only, let's say, the biological or biophysical processes that are going on in the sample, but eventually we can think about to learn something also from other methods. So we, as already mentioned, in 2015, Boyden realized this expansion microscopy method that was at the beginning applied mainly to brain sample and tissue sample, in which let's say that are more challenging in terms of improving resolution and in terms of, for instance, following the network in the brain. And we were so immediately very excited about this method, and in fact immediately we decided to go for one of our regular schools to invite Boyden and one of his postdoc from his lab came in our practical school to teach us how to make expansion microscopy. And from there we were excited and also a little bit skeptical, in fact, because we say, well, how we can apply this to nanoscale? The expansion will work in a correct way also at the nanoscale, or is just, more a macro phenomena that could have some troubles eventually at the nanoscale. So let me tell you some more about the concept. So in general, when you have a microscope, you have a response function from the microscope, like the PSF. So if you have a point source, you see this point source, it's of a certain size that depends on the diffraction limit. If you have 2 point sources that are too close together, you cannot distinguish them, but you can apply STED, for instance. Then the response function is smaller, so maybe you can distinguish the two objects that are a certain distance. But instead of, we can, let's say, change completely the paradigm and say, well, now we want to make the 2 points apart from them, and so now we can, in fact, distinguish. And this is what the expansion does. So we can move, let's say, the fluorescent marker and the, let's say, the relative position of the molecule we are interested in apart, and so we can now distinguish their position. And of course, since they are still fluorophores, we can also apply STED, and so we will improve even better the resolution of our microscope. Or we can investigate what happens and which is this expansion factor. So of course, nowadays there was a big interest in this technique, as Johan also showed, and so there are many ways, and now also with lipids, as Johan shows, we can use expansion in possibly all kind of sample, and also all kind of fluorescence, let's say, labeling. So the expansion process requires several steps, and the simplest case, and maybe the most let's say also used eventually case, you of course you have to start with a fixed sample, because you are going to let's say change a lot of the nature of the sample, and so you have to fix the sample, and you have to label. Or you have already labeled eventually if you have fused fluorescent proteins. And the labeling is quite conventional, could be quite conventional as your choice. In general, it should be a labeling for super resolution. And of course, since we make fluorescent the sample, and we can apply STED. So for each step, we can think about using STED to monitor what happens in the sample. So you can then pass to the second step, that is gelation. So you have to introduce the monomer of the hydrogel and make it, let's say, link to the fluorescent molecule, to the proteins, so that the fluorescent molecule will stay in the relative position respect to the original position of the proteins that you want to label. And also at this step, since the fluorescence is still there, we can image and see how it looks the sample. And so we can do after digestion the same thing. So digestion is needed because you are going to expand the sample, so you don't want to have constraint in the expansion. So like a protein that are, let's say, by nature used to keep the shape of the cell. But you want that the cell shrinks and let's actually expand of about 4 to 5 times, so it should be free to expand. Otherwise, you can have artifacts. And in fact, if you don't do this properly, you can see at this step you can have some artifact if you don't properly do the digestion. You have, for instance, cells still attached to the surface and part of the cell not attached, and this comes like out already somehow expanded at this step. So of course you have to have some practical trick. So you are going to expand of 5 times, so it could become very huge sample after the expansion. So maybe it's good to take small pieces, and you can even monitor the expansion, since the expansion comes because of you adding water, milky water, and so then you get the expansion. You can do this under the microscope. You can look what it happens actually during this step. But what happens at the nanoscale? So, and how is it, let's say, homogeneous still? And let's say the expansion factor is the same at the nanoscale as what we see at the macroscale. So we thought about monitoring this using STED microscopy and using nuclear pore complex as the ruler to see how much is the expansion. And of course, we can do still all the other way to measure the expansion. So we can look at the gel size, we can look at the inter-cell distance, and we can statistically measure the nuclear pore sites. and eventually how they are distributed, the subunit. The usual way to measure the expansion is to measure the sample before the expansion and after the expansion. And you will see, and you overlay the image before and after the expansion, and what you can see is the match of the pre and post expansion, understanding which is in fact the expansion factor, and also to see if the match is reasonably in the error of the distortion, so that no match distortion happens. But then what happens at the nuclear pore size and at the nanoscale level? So if you look at 3 points in the step, like pre-expansion, post-digestion, that we saw it was a little bit critical, and post-expansion, we can monitor by confocal imaging these 3 steps, and we can monitor by STED imaging these 3 steps. So, in fact, also even before the expansion with STED microscopy, we can start to see the hole, so the ring of the nuclear pores, and of course, after expansion in confocal, this is also possible. So in these 2 images, in fact, are very, let's say, similar in terms of resolution, but then we can have also the combination that brings even at another level the resolution. And we can see here that when we combine post-expansion and STED imaging, we can really see how we label the subunit, how many subunits we labeled, how many are still there after the expansion, in fact. And using a statistical approach, since it's a very regular object, a nuclear pore, we can use many nuclear pores to see statistically if we have all, in fact, all the subunit, if they are correctly spaced, angular spaced, and we can measure the sites. And so since we know the size of nuclear pore, we can measure the expansion factor. So all of this to say that, in fact, as also Jon mentioned, expansion works very well and keep let's say, the shape of the original cell and original tissue with a very good approximation that is about the 2% to 3%. And this happens also at the nanoscale in a very similar way. So we have a new tool, and we have a tool to improve the resolution, that is expansion, that can be combined with STED, and now we can think also to reduce the STED power, and so have less photobleaching when it's already expanded, because we don't need any more, let's say, the full power, because and STED is tunable. While, for instance, with expansion, let's say, it's better to go to the maximum expansion. With the STED, we can, let's say, tune the power, so we can decide that we reach already the resolution that we like in the sample. And so we can make even more fancy images, and so we can see the hole in the microtubules, or we can use a nuclear pore as a second eventual label to measure the expansion without doing this time-consuming approach of imaging before and after the expansion process itself. But now, so we use STED to investigate a nanoscale, and so we have a tool like an instrument that has 2 kinds of beam. As a Gaussian beam and a donut beam, or another shape, but with a 0 at the center, that allows super resolution if you perform stimulated emission. But can we do something else with this kind of with these 2 beams, maybe towards level 3? Well, since you have these 2 beams, you can apply one of these techniques, like switching laser mode or fluorescence emission difference. The acronyms are different, but the practically technique is the same. That is about taking an image with the Gaussian shape and another one with the donut shape of the same object, same power. Now we are not going to saturate, we just do linear fluorescence excitation, for instance, and we do a subtraction. What will happen is that you get a better resolution, maybe. If you look at the profile, in fact, if you do just a subtraction, you have over subtraction, strong over subtraction, and this is not good for imaging because you cannot have negative values. So the way they implemented already is to have a coefficient that allows to reduce these negative lobes, but of course this value in general, apparently from literature, depends on the kind of sample you are going to look. So if we look at the beats, for instance, and you do different value alpha values, you see that any value is good and even one looks good because it's sort of thresholding effect more than a real resolution improvement. If you go to a fluorescence image, densely labeled, these appear immediately much worse, in fact, because if you subtract with a value that is too high, you see clearly that you lost most of the information of your image. So we came out with an idea to be independent by the object that we are going to see and to use the information that we already have, like the intensities of the two images we acquired. So if the images are normalized, we have some normalization factor from -1 to 1. And what we do for the value that the coefficient that we should subtract the donut, we say that is the intensity of the Gaussian image in that pixel minus the intensity on the donut pixel. And so that we get a subtraction finally of the two images that is pixel-wise dependent and depends on the intensity, relatively intensity of the two images in that pixel. And so as you can see, this value, this coefficient will vary along this line in case of this line profile. And of course, if you do this, the negative lobes will be much reduced, and anyway, the resolution will be kept, fully kept. If we compare, for instance, with an alpha value of 0.6, that is already a lot. So what we have to do is to take an image with the Gauss shape and with the donut shape, and then we subtract using as coefficient exactly the one that I show you. This means that the coefficient we are going to use is pixel by pixel. You see here different because it takes into account the original images. But as you can see, the distribution of these values, in fact, are always around the value that we expect to use, properly use for such kind of images, so around 0.5. So now we apply to different techniques, but in fact, has not so much interest if you use for fluorescence, because in fluorescence you can do many things. However, we compare with it. But when we have some images like reflection, well, there you cannot do so much. And so you can think about using donut subtraction and use the donut as any way to improve the contrast and the resolution of your image. Like, for instance, also in second harmonic generation, where you cannot apply again, as in the reflection case, any other super resolution technique eventually. Or unlimited super resolution technique, better. And so, of course, this can be done also in the third dimension. But so this has some. So as conclusion is simple. You have already the microscope. You can apply. It's low photon dose. The resolution is not incredible. The improvement is already relatively improved. but we can apply without the convolution. It's already an improvement in the imaging. And so now, anyway, this is only linear improvement. But what about doing something more, and also in something that is not fluorescence, like, for instance, graphene? So we thought about applying a pump probe technique that is so mainly a spectroscopical technique. I think you will get much more insights also in the following talk today. I think from Dario, for instance. And so in this case, you have two beams, one that interact with the sample, and the second that investigate, which is the status of the sample after, let's say, the first interaction. So to do this, you normally use very short pulses, because you want to investigate actually very fast, normally very fast transient time in the absorption, and so you are dealing most of the time with the ultra fast laser like titanium sapphire source, and of course these lasers are also good to do to photon imaging and to photon fluorescence or multi-photon fluorescence imaging. That is, in fact, a label-free approach in the sense that you are exciting endogenous fluorescent molecules. So you are going to, like in this case, to see the endogenous pigment of this pine pollen, but you see also something else that has an absorption, but not maybe an emission, and can be resolved in 3 dimensions by this technique. So how to then bring this technique to super resolution? Well, so this technique can be implemented in several ways. One way could be to look in transmission through the sample. It's easiest. You have a pump beam and you have a probe beam, and and you are collecting this probe beam. And in the case of the graphene, we will see this is ground state depletion. So you both the beams, for instance, undergo the molecule undergo or the matter undergo absorption with both the beam, and so since the pump is modulated and the probe is not modulated, if your detector sees such a modulation, this means that the probe, so this is such interaction with the pump with the sample. So in fact, as you can see here, what we are measuring is this kind of modulation. And what happens if we saturate the absorption introduced by the first beam, and if we do this by a spatially defined shape with a 0 at the center? So if this transient absorption is saturable, of course, what will happen is that we bleach in the sense that the sample becomes transparent at the border of this pump. And so the probe will see such a kind of modulation only at the center. This is because the saturation will happen all the time, so it's not modulated. So the modulation that now is still present will come only from the very center of the donut. And so the probe will see such a modulation. So then we need a confocal microscope, a scanning microscope anyway, to do the imaging. And we use as excitation, that is not exactly excitation, a pump and a probe beam synchronized, and we do a modulation with the electro-optical modulator, for instance. And then we add the second beam with a donut shape. Thanks to the vortex faceplate, we combine, so the third beam in the scan head, and we perform, as it happens for the standard imaging, we perform the imaging. Here now, however, we are not detecting anymore the fluorescence or the emission from the sample, but just the variation that happened to the probe beam. So graphene, it's interesting for this approach. Is probably finally the simplest way to also to prove this kind of approach, because it has so it is not fluorescence. First of all, if this is a real single layer graphene CVD, clean, with no other layers and so on, no dust and other defects. So the absorption of graphene, it's quite long and little, I would say, along quite a broad range of wavelength. So, for instance, in a conventional, let's say, now we use a chameleon from Coherent, but any titanium sapphire laser with an OPO can provide two lines in this range. So both will be absorbed by the graphene, and so we can, for sure, we can do the imaging, we can do pump probe, we can do an XY and XZ. We can also combine with the cells, maybe grown on the graphene, and we can get the fluorescence from them. So we can have also a multi-channel, multi-modal approach to this imaging, and we can try to quantify some properties of the graphene, well-known properties of the graphene. So we can see also graphene flakes, so other layer of graphene growing on the single layer, and of course it's we can even think about counting the number of this layer, because we have a linear dependency in the signal, and of course we can also do the spectroscopy with our limitation, in the sense that we have sort of long pulses for such a kind of experiment, because we start with 140 femtoseconds, but we have a lot of glass because of the microscope. So we end up with pulses at the sample that are about 300 femtoseconds. But anyway, we can move the probe in time, and so we can measure the decay time of the graphene, that is about less than 2 picoseconds. But what we want to see is super resolution. So we don't want we want to have a contrast, a strong contrast, and see an high resolution image. We need to know saturation, so we can measure where it happens in power, the saturation, by doing this power curve with probe and with pump and probe, and then we add this to this third beam to see which is the effect of this saturation. So now we have the pump that is modulated, the saturation pump is not, and is Gaussian in this case, and probe is not, and is Gaussian, is what we are looking at. And we place the saturation pump in 3 different positions, and we see which is the decrease in the pump probe signal once we have this saturation pump in 3 different temporal positions. And we see the ratio, you see by color, the ratio between with no pump, with no saturation, and with saturation. And as you see, we are almost at ISAT. When we are 0.5, we are at ISAT for this kind of combination. So where is the best suppression of the pump probe signal in time? So we can now fix the position of pump and probe, because we know we want to let's say to have the maximum signal to noise ratio. So we set pump probe at time 0, and we check which is the behavior moving the saturation pump, and which is the power, and how it behaves with the change of power. And in fact, if you look at three different positions, three different delay of the saturation pump, we see that ISAT, so our ability to improve the resolution is much higher, and the power we need is much lower when we are, in fact, we have all the three beams around the time zero, although with a slight shift. Then we can try to image, we can do pump probe and saturation, and we see the improvement in resolution. In this case are, let's say, small defects or multiple layer, and we can see on large scale the improvement in resolution. We can do somehow fast imaging that would not be possible with, let's say, for instance, with the near field techniques. And we can reach a quite high resolution, like 90 nanometer, considering that we are using as a probe 1000 nanometer. And we can do more, because now, since we have lateral improvement in resolution, we can count better even the number of layers in these flakes. So we can better see how many layers. So we can let's say speculate on the thickness of this layer, knowing let's say of these flakes, knowing the thickness of a single layer. So let me conclude, thanking all the group, in particular the people that contribute to the work that I show you today, and Alberto Diaspro, that is directing all the department. Thank you very much for your attention.